welcome to CEC lectures. Myself Dr. Preeti Chakmani. I am an associate professor from Department of Computer Science, Aryabhatta College, University of Delhi. So presently in this series of advanced data structures and algorithms, in our previous lecture we have seen about, we have seen in detail the quick sort algorithm. So basically in the previous lecture we established a platform, a stage to start with our tweaked version of this quick sort algorithm, which is better known as randomized quick sort algorithm. So let us recall this quick sort algorithm quickly, and then we will be moving on to today's agenda, which is randomized quick sort. So when we say quick sort algorithm, as the name suggests, it is a sorting algorithm which is used to sort any array. Let us say the array, the lower limits are p and r, and I am assuming p is always less than r. And the strategy on which this quick sort algorithm is based is basically divide and conquer. So if we say the divide, conquer and combine steps, let us see how these steps takes place in this quick sort algorithm. So in the divide step, we are partitioning this array which is starting from p to r, a of p to r, into two. It could be possibly two empty sub arrays. The first sub array is from p to a particular position which is says q minus 1, where every element is less than a of q. So every element is less than one particular element, and that one element is known as pivot. And in the right side of the partition, or in the another partition, the values are starting from q plus 1 to r, where a of q is less than equals to every element. So in the left side, all the elements less than that a of q, which is nothing but the pivot, and on the right hand side all the elements greater than that pivot. Now divide and conquer, as you all aware that this is a strategy which goes into 3 steps. This next step which comes is conquer. So conquering is actually sorting these two sub arrays by recursive calls, by dividing again and again these arrays into the smaller partitions, into the smaller sub arrays, and then sorting these two arrays using recursive calls. And finally it is the step which remains is about combine. So combine here, we do not need any work in order to combine, because all the sub arrays are sorted now. As soon as this recursion is ending, we are going to have a completely sorted array. So this was divide, conquer and combine. And if we look into the quick sort algorithms pseudocode, we will be having quick sort. This is performed on 3 parameters. One is a, which is the array, another two, which is p and r, are the limits. So if p is less than r, or we can say this is going to be a base case, that till your p is less than r, you are going to partition this array into two different arrays, and the result of that partition, which is the point of partition, is returned into this variable q. And now you will be applying the quick sort algorithm on this array, on the left part of the array, which starts from p to q minus 1, and also on the right side of the array, which starts from q plus 1 and ends till r. So this was actually kind of, we can say, a background of quick sort algorithm. Now actually, why do we need randomization technique or randomization to be included in this? So if we talk about the partition of this quick sort, so each partition here is basically theta n time complexity. So we can easily see that it is the only component that grows with n, and it is a for loop that iterates proportional to the number of elements in the subarray. And this is what we have the pseudocode related to it we have seen in our previous lecture. And the runtime of the whole array depends on the partitioning of the subarray. So now that partition may generate kind of the best case complexity, or this partition can generate the worst case complexity, or even this partition can generate an average case complexity. So depending upon this partition, how these worst case, best case and average case are determined, let us see that. So, the worst case occurs when the sub arrays are completely unbalanced. Completely unbalanced, that means there are 0 elements in one of the sub arrays and n minus 1 elements in the other sub array, and nth element is your pivot, which is in neither of the arrays, and the single pivot is not processed in recursive calls. So, one portion of the array or one partition of the array is completely empty, another partition is having n minus 1 elements, and this is going to recur every time. And please remember or please recall, this is kind of, if we are going to formulate this into a recurrence relation, this will be a very familiar recurrence relation, which is equals to the recurrence relation of insertion sort. And here you can see what kind of recurrence relation it results into. So, T of 1, which is the total time for sorting n elements, is equals to T of n minus 1 plus T of 0. So, this is actually the we can say size of the two partitions plus theta n. So, theta n is for partitioning thing. So, for partition we have a complexity of theta n. Now, next thing which we need to sort is T of 0, that means the partition in which no element is present, and the next thing or we can say the last thing which we need to still sort is n minus 1, a subarray of n minus 1 elements. So, in order to compensate that, we have written T n minus 1. So, the recurrence relation is T n minus 1 plus T of 0 plus theta, and this is exactly the recurrence relation of insertion sort, because in insertion sort we are just kind of we can say we are sorting one element, and n minus 1 elements are kind of we can say kept behind or left behind in order to be sorted. So, here we can say T of n minus 1 plus theta n, because T of 0 is not going to occur any time complexity, and if you solve this by Master's method or even for from a recurrence tree point of view, it is going to give us theta n square, which is exactly the complexity of insertion sort in the worst case thing, and here theta n square is also the worst case for the quick sort algorithm. Now, what kind of data or what kind of input samples are going to lead to this kind of behavior? So, this kind of behavior will kind of will occur when your data is already sorted. That means the pivot is always either the minimum element or the maximum element. So, we are going to get partitions of size n minus 1 and 0 each time. So, if you are going to say your array is sorted in increasing order, and if you are going to take the last element or even the first element as the array as the pivot, sorry. So, if your first or last element are occurring as pivot and the elements are in sorted order, the partition which we are going to get will be of size n minus 1 and size 0, and this will happen each time. And because of this, the quick sort will end up in order of n square, which is the worst case complexity even on sorted data. But if you recall, the insertion sort that actually does better on a sorted array, which is nothing but order n. Order n square is the worst case complexity of the insertion sort, which is obviously not for the input samples of increasing or decreasing or already sorted array. Already sorted array gives the best case for the insertion, which is order n, but already sorted array here in quick sort is going to result in a worst case complexity, which is nothing but order n square, and the partitions are I cannot say these are unbalanced. One partition is completely empty and another partition is having n minus 1 elements, and this is happening with every partition. This is happening every time. Now, after this worst case, if we talk about the best case occurs when the subarrays are completely balanced. That means we can say they have approximately n by 2 elements. Why I am saying approximately or about n by 2 elements? Because pivot is is to be taken care of. So, two portions of n by 2 size, of approximately n by 2 size, this gives a feeling of again a familiar recurrence relation, which is nothing but of merge sort, and this is going to be the recurrence relation for your we can say a balanced partition in which there are two arrays. So, 2t and each array is of size n by 2 approximately. So, n by 2. So, 2t n by 2 for those two partitions of n by 2 size each, plus theta n, that theta n, as I have already told you in the previous case, that theta n accounts for the partition thing. And if you solve this recurrence relation, or now some of the solutions to these very common recurrence relations must be on the tips. So, this is ending in theta n log n. So, this is going to be the, and theta n log n, please recall, is the complexity of the merge sort for every case, whether it is a best case or a worst case or maybe an average case of merge sort. This is going to give us the equal complexity or the same complexity in every case, which is nothing but n log n, and this is the best one can do in the worst cases of your comparison based sorts, which is nothing but theta n log n. Now, when we talk about one side which is having equal partitioning, another side is having a partitioning resulting in the subarrays of 0 and n minus 1 size, we can have something in between these sizes. All those partitions are also they comes under the category of unbalanced partitioning. So, for example, when we see the effect of unbalanced partitioning, we say that it turns out that the expected behavior is closer to the best case than the worst case. Now, this is a very kind of important and a punchline as far as your quick sort is concerned. I am repeating it again. It turns out that expected behavior is closer to the best case rather than to the worst case. So, in general scenarios of other comparison based sorting algorithms, the expected behaviors are generally kind of closer or as bad as the worst case, but here the situation is different. The expected behavior is closer to the best case. So, we will be taking some examples in order to see that why these expected cases are not as worst are not as bad as the worst case. So, for example, instead of that 0 and n minus 1 split, let us take a split which is having one element, which results in one element in one particular subarray and all other elements in the different another array, or let's call it is 1 to 9 split. So, 1 to 9 split is something like that. Suppose each call splits the data into 1 by 10 and 9 by 10. So, 1 by 10 and 9 by 10, this is actually highly unbalanced. So, is it going to result in the horrible performance? I would say no. Why? Let us see that. So, if you can see the recurrence tree of this kind of highly unbalanced partitioning. So, we have n 1 by 10 n on one size, n by 10 n on another size, and then this is this kind of partitioning in recursive we can say recursive steps. So, every time, so 1 by 10 n is again partitioned into 1 by 100 n and 9 by 100 n. Similarly, 9 by 10 n is again partitioned into 9 by 100 n and 9 by 100 n and 81 by 100 n. So, this is what it is. So, every time we are resulting in the partition which is of 1:9 kind of a ratio, and that is why we have called it as 1 to 9 split. So, here if you can see or if you can observe this recurrence tree very carefully, you can see that we have log n full levels, log n with base 10 obviously, and log n levels but with base 10 by 9, that those are kind of non-empty levels, we can say, not full neither empty nor full nor empty, but non-empty. As long as it is a constant, the base of the log does not going to affect the asymptotic results, and here if you can see log n with base 10, so 10 is again a constant, and log n with base 10 divided by 9 both are constant. So that means they are not going to kind of affect the asymptotic complexity, and any split of these kind of constant proportionality will yield a recursion tree of depth theta log n, as we have just seen in the figure. So, by the derivation, if we can see that log n with base 10 by 9 is equals to log n with base 2 divided by log 10 by 9 with base 2, and if we put on these kind of values, we end up with theta log n, and the whole values and the the constant which we have taken C as the constant is equals to 6.5788, and ultimately we are ending up with theta log n. So, the recurrence for this kind of which we call highly unbalanced partitioning and its corresponding solution is, if you can see, this total time in order to sort or in order to solve the problem of n elements, Tn is less than equals to T 9n by 10 plus T n by 10, which is the kind of partition size 1:9 split, as we have declared in the just before, plus theta n for the partitioning, and ultimately it will end up in n log n. So, Cn kind of levels, and here we have theta log n. So, total recurrence and its solution is order n log n. So, these are actually, we can say, kind of somewhat surprising results, that even in the so called highly unbalanced partitioning, which is 1:9, my results is, or my expected result of time complexity is as good as the best case, which is n log n, and it is not going to be on the side of the worst case complexity, which is nothing but order n square. So, now quick sort with this virtue is going to be a very peculiar algorithm, in the sense that whatever the expected and the average behavior is matching towards or is going towards the best case side rather than the worst case side, and this is opposite of many other sorting algorithms, we can say. So, from here now we have understood that even very unbalanced divide and conquer are so very useful when we talk about time complexity. And with random data, there will usually be a mix of good and bad splits throughout the recursion tree, and a mixture of worst case and the best case split is asymptotically going to be same as the best case. So, here if you can see in the figure, here again n is divided into 0 and n minus 1. This is the kind of, we can say, the first level is a worst case split, but then n minus 1 is again divided into kind of, we can say, two balanced partitioning. So, n minus 1 by n minus 1 divided by 2 minus 1 on the one side, and n minus 1 divided by 2 on the other side. Or it could be a straight good split which gives n into n minus 1 by 2 parts on both the sides. So, both these both these splits, one which is a combination of best and the worst case, another one which is obviously giving me the best case, these trees have the same two leaves, but the tree which is on the left side is having an extra level which increases the height by height of the tree or by a factor of 2, and this constant will disappears in the asymptotic analysis, or we can say theta analysis. But both these leaves, both these trees results in order n log n, though with a larger constant for the left. So, ultimately it is going to be asymptotically, it is going to be n log n for both the sides, but for the left, which is having a mix of best and the worst case, constant could be a little larger, but it will result in theta n log n. Now with this we have kind of completely set the stage for randomized quick sort. So till this point we have understood what is quick sort, that was in our previous lecture. Then here in detail we have considered all the partitioning, which is the best case partition, which is the worst case partition, and the expected case, even if it is kind of highly unbalanced. What do we expect? We actually expect good average cases behavior if all the input permutations are equally likely. But what if it is not so? So, in order to get a good performance, or in order to get the better performance on sorted or maybe a nearly sorted area, nearly sorted data, we can randomize the algorithm to get the same effect as if the input data were random. And how are we going to do this? This can be done with the help of randomized quick sort. So, I am just repeating this. In order to get the better performance on sorted or maybe nearly sorted data, we can randomize the algorithm to get the same effect as if the input data were kind of random. So, instead of so what can be the ways of introducing randomization? So, one idea could be explicitly permute the input data, and this idea, believe me, is going to be very, very expensive. So, instead of explicitly permuting the input data, which is an expensive affair, randomization can be accomplished trivially by the random sampling by one of the array elements as the pivot. So, we are going to select one particular element randomly, and we will be swapping it to make it pivot. So, if we swap the selected item with the last item, the existing partition procedure, that existing partition as in the partition procedure which we have seen for the quick sort, that procedure will definitely applies. And here are the kind of two portions of not the quick sort, but the randomized quick sort. So, in order to have the effect of randomization, so randomized quick sort is going to call randomized partition, and obviously the recursive calls to be will be for randomized quick sort. Rest every fundamental is same. So, A, P, R, Q is the result of randomized partition. Then randomized quick sort for left side is from P to Q minus 1, and for right side it is from Q plus 1 to R. Now, if we look into randomized partition, this is actually calling partition, but before calling the function partition, this is giving an effect of randomization by choosing an I, which is a random element between P and R, or we can say which is a random index between P and R, and then A of R, which is generally our pivot, is exchanged with that A of I. And now this partition will happen on A, P and R, while your R is already kind of exchanged with I. So, now even in with this kind of situation, your an already sorted array is going to give us an kind of an expected behavior, or an we can say average behavior. So, when we say quick sort and the randomized quick sort, the whole difference depends upon the chosen pivot elements. Since the worst case scenario occurs when the pivot is the smallest or pivot is the largest element and your data is already sorted. So, we try to reduce this case, or we try to reduce happening of this case by using a random approach for choosing the pivot element. So, if compared, you know, kind of we can say technically it is only the choice of the pivot element which gives a difference between the quick sort and the randomized quick sort algorithm. Rest everything is, you know, same for both of the algorithms. So, by you know, introducing randomization into our choice of pivot, we have actually, you know, kind of you know, decreases, we are going to decrease the chances of the worst case happening. That is what the agenda is, and more of the average case occurrence chances are increases. So, the average case is as good as best case, and if it is in the best case, then the problem is not at all there. So, best case and average case, we want them more to occur, and we want our worst case to you know, happen you know, relatively in the lesser number. So, this is what actually the difference between quick sort and the randomized quick sort is. In this lecture we have seen why do we need a randomized quick sort, what are the, you know, kinds of, or what are the, you know, situations of partitions which occurs from the naive quick sort algorithm, and how it is going to you know, motivate algorithm designers for introducing a randomization and then come up with a randomized quick sort, which is kind of a tweaked version of the quick sort algorithm. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. Thank you for the patient hearing. I will see you in the next lecture. Till then, take care. Goodbye.